Hi and welcome to a new Voltlog. Today we are taking a look at this 300 watt pure sine wave inverter, which was provided for free by Banggood for the purpose of this video. It's practically the first inverter that I own, and I'm quite intrigued by these pure sine wave terminology. I'm curious to see if it really produces a real sine wave on the output, or if it's just a few steps of voltage in the shape of a sine wave. Like mentioned, this is a 300 watt model with a 12 volt input and a 220 volt output. So let's take it out of the box and take a closer look. So inside the box we get the inverter, we get a pair of chunky cables for the input and the spare fuse, and an instructions manual. By looking at the inverter we can see the universal socket for the output. I believe this will work with any socket, US, European, even Australian, and it even has the protection panels to prevent you from accidentally inserting any sharp objects into the socket. We also have an USB port output. We'll be measuring the ripple voltage and the current output on this port a bit later. The labeling on the inverter just looks like it has been compressed slightly on the horizontal axis. Wow, it has intelligent cooling. I guess that means it's a temperature controlled fan. We'll see about that later. The input terminals feel okay, not the best in terms of quality, but I think they will do the job. By taking a quick look at the manual, you're supposed to create a common ground point on the inverter, but there is no ground point connection on the enclosure, and there is paint all around, so it will be pretty hard to get a good connection with the case to create a common ground. I guess I will run this with a floating ground. I'll do a few tests on this inverter and then I'll also do a teardown so we can take a look inside. But first I'm most interested on how the output waveform looks like. So I'm going to power the inverter from this 12 volt lead acid battery, and I'll connect my scope to the output of this inverter to take a look at the output waveform. So I have my scope set to 100 volts per division times 10 on the probe. The inverter is turned on. Let's zoom in on the waveform. And it really is a nice looking sine wave with a frequency of exactly 50 Hz and an RMS voltage of 227 volts, which is okay considering it's not loaded right now. Let's try to zoom in on the waveform even more. And we kind of start seeing some steps, but nonetheless it's a perfect sine wave. I mean, I've seen signal generators that had a sine wave looking worse than this one does. So it's a pretty nice sine wave this inverter produces. I'm also interested in the startup behavior, so I've set the scope for single capture, and now I'm going to turn on the inverter. And we can see the voltage is slowly rising up to the 227 RMS, but I don't see any overshoots or anything funny going on. It's just that it takes approximately 3 seconds for the voltage to reach the maximum voltage. Not sure if that's a feature or a bug. Not sure if they implemented something to have this slow ramp up of the voltage, but it should be okay. Now let's also check the shutdown behavior with no load. It's not bad. I think it just dropped the first sine wave that followed the shutdown. It completely turned off. So that's alright. Now for the load test, I won't be able to test this inverter at the full 300 watts rated power, because I would need to provide about 25 amps at the input, and I don't have a power supply capable of supplying that on the 12 volts rail. But we can test at around 200 watts, and I've created this setup with 3 incandescent light bulbs. This setup draws approximately 200 watts, 215 watts, and we can use this to load the inverter, check out the waveform when it's loaded, and also see how it behaves with a load. If the fan starts, if the enclosure starts to get hot, everything that needs to be tested under load. And we can also measure the efficiency of the inverter by measuring the input voltage and current and the output voltage and current. We can calculate the difference between the input and the output power, and so we obtain the efficiency of this inverter. So it appears my battery is too weak to be able to supply the current to the inverter, and the inverter starts beeping and it resets because the input voltage goes below a certain threshold. Here is how it behaves. So the light bulbs start to glow. The waveform looks nice even under load, but there it goes. The battery cannot supply the current and the inverter will turn off soon. It makes this annoying beep. I guess that's an alarm feature to let you know that the battery voltage is going too low and you'd better turn off the inverter to prevent killing your battery. So I'm going to switch to lab bench power supply that will be able to supply more current to the inverter. So right now I'm using my two Gopher power supplies in parallel to supply the inverter with more current. So it should have been obvious from the start that with a 200 watt load on the output of the inverter, I need to have maybe 20 to 30% more on the input of the inverter. It should have been obvious that that small battery or a couple of power supplies capable of 10 amps in total are not able to supply 250 watts to this inverter, but I don't know what I was thinking. But I quickly realized that, and I had to remove two of the light bulbs. I'm left with just one light bulb, which is approximately 70 watts on the output of the inverter, and this way I can power the inverters from the small power supplies that I have. I really need to get myself a more capable 12 volt power supply on the bench, something like one of those server power supplies that can output an excess of 1000 watts on the 12 volts rail. But anyway, just the light bulb is sufficient to test this inverter. Unfortunately, I won't be able to test it at full load, but we can take a look at the waveform and we can see it still looks like a nice sine wave. The frequency is constant. The voltage is okay, has gone up by 2 volts. It's 229 volts RMS right now, but the waveform still looks pretty clean, and I do not have any filtering turned on the oscilloscope. So right now I'll move on and place some multimeters on the input and on the output of the inverter to measure its efficiency. So in my setup, the O1 and the unity meters are measuring the input voltage and current on the inverter, and the MetroHit and the Flux 87 are measuring the output voltage and current. So we'll use these values to calculate the efficiency of the inverter, and I will annotate that on this video. There is no mention of an efficiency figure in the specs of the unit or in the instruction manual, so I'm just going to take that as a reference, considering the usual converters that I've worked with in the past, and I'm going to go ahead and say 88.5% is not a bad efficiency figure. It could be better. I think it could be in the 90 to 92% range, and it would be perfect then, but certainly not bad. The USB port seems to only work up to 0.6, 0.7 amps. After that, the output just cuts off. It's like it goes into some kind of protection. It may be a thermal protection, I don't know. I'm starting to think they're using like a 7805 in there, and it gets hot pretty quickly. Not sure, but just so you know, it's only good up to 500 milliamps. Anything that goes above will trigger the protection sooner or later. You see, even at 500 milliamps, it can't do that continuously. It's probably a small regulator inside that gets hot, and we'll check that later during our teardown. And this is how the ripple voltage looks like with the dummy load set for 500 milliamps on the USB port power output. We're getting something close to 500 millivolts peak-to-peak noise. And this is with no load. Now for the teardown of this inverter, we previously saw it really does produce a true sine wave output, so I'm expecting to find some kind of microcontroller that is switching the MOSFETs according to a lookup table to create that sine wave. At least that's what I'm expecting, because I think you could also achieve the same result with some kind of specialized ASIC driver that has an internal lookup table, but I think it's cheaper to just use a microcontroller, something like a Chinese STC microcontroller or even a PIC microcontroller that is going to be switching those MOSFETs according to a lookup table. So to open this, looks like we need to remove these side panels. Let's start from the input side. Wow, it really is messy on this bottom side. Looks like they've used some nasty flux for soldering the through-hole components, and they haven't cleaned any of it off the PCB. But from the top it looks like a pretty clean construction. The first thing that I'm curious to check is this USB regulator. Let's see. Yep, I think I was right. I can see the 7805 regulator for the USB output. There is no heatsink on this TO220 package, so drawing 500 milliamps from this port will put this regulator into thermal shutdown pretty quickly. So I've taken a closer look at this thing. The build quality is not very good. I mean, there is lots of flux residue on the bottom. As for the cables, we can see some strands broken off from this input cable. I think on the output we're pretty close to having the same problem. It's a mix of surface mount components with through-hole components. And I was wrong on the topology when I mentioned earlier that I think they are using a microcontroller. They are in fact using an ASIC. And I've drawn this kind of block diagram of how this whole circuit works. So we got DC 12 volts coming in here through this fuse with some filtering caps, which I haven't drawn in here. then the voltage gets stepped up with these with this SG3525 PWM power supply controller with a couple of MOSFETs through this transistor. It gets stepped up to 390 volts, and it's then rectified and filtered with this capacitor right here. So on this point we have 390 volts DC, and then with the help of this ASIC called the EG8010, which is specifically designed for this kind of application, they pretty much followed the diagram from the datasheet of the chip. They're using the same drivers for the MOSFETs, the IR2110S. They're using the exactly same MOSFETs, IRF840, and exactly the same configuration to obtain a sinusoidal output. And we only need a filtering choke on the output, exactly as shown in the datasheet of this ASIC chip. So I was wrong thinking that they might be using a microcontroller, when in fact there is this very cheap ASIC that they can use, and they do away with the programming and all that stuff which is involved with microcontrollers. Pretty sure it's way cheaper to use something like this. And I believe this chip, yeah, this chip even has a pin for controlling the fan. So that's why they have that intelligent fan control specified on the case of the inverter. This chip does it all internally. And it's not only the chip, they are using exactly this module. I believe this comes directly from the manufacturer of this ASIC. They sell this module complete with the drivers and everything, and we can see a small bodge right here, maybe to adjust their output voltage or something like that. They solder in a different resistor in here, and we can see some flux residue left. So the manufacturer of this inverter buys this module and just solders this module onto the inverter board. And right here we have another module with the what was it called, the SG3525 controller, which controls the high voltage step up power supply on the input. So that's pretty much the architecture of this inverter. There might also be a secondary winding on this transformer for powering the 7805 and the support circuitry on this board, but that's pretty much it. But before putting everything back together, I'm going to use some flux cleaner and remove this flux residue from the board, because I just can't leave it like that. It's disgusting. I don't like keeping my equipment in this condition. And now to give you my final opinion on this product, I would rate it only as good enough. The build quality has some problems. We saw flux residue on the PCB, which was disgusting. We saw one hang low capacitors. The way they are attaching the high current wires to the PCB doesn't inspire confidence in long-term usage. Also, I didn't saw any insulation between the metallic enclosure and the bottom of the PCB with the exposed contacts. It's just stuff that you usually find in higher quality equipment, and it's there for a good reason. Also, the USB port is useless with the 7805 behind it. That just gets into thermal overload pretty fast, so you can't use it for any real purpose. The price for the inverter was $55, which is not a lot, but it's not cheap either to throw it away. So I wouldn't recommend getting one of these inverters unless you have had others and you think this one looks better on the inside. It certainly produces the through sine wave output, and although not fully tested because of my limited possibilities, I think it will reach its full rated output power. During my test at 70 watt, the fan didn't even start. So I think it is capable of its full rated power. So that was all for today. I hope you enjoyed the video. If so, please hit the like button below and I will see you next time.